Okay, this will be the last lecture on adsorption. We will finish this chapter. It's a little longer than the first lecture. Today we start talking about the adsorption isotherms. An adsorption isotherm describes the relation between the activity or concentration at equilibrium. This is extremely important. Remember, at equilibrium of the adsorptive and quantity of adsorbate on the surface at constant temperature. So we have two things: the adsorptive, how much there is in the solution that is surrounding the adsorbent, and how much quantity moved from the solution to the adsorbent surface. The relationship between them, that's how we will draw it in a curve we will call an adsorption isotherm. Adsorption can be described by four general types of isotherms: S, L, H, and C types. We will look at each one of them and see the different characteristics of them. With an S-type isotherm, the slope initially increases with adsorptive concentration, but eventually decreases and becomes zero as vacant adsorbent sites are filled. Vacant adsorbent site, of course, the adsorbent have positions or sites where the ion or molecule will be adsorbed to them. These are the sites. Vacant, that means there is no molecule or ion on that site. We call it a vacant site. So as the adsorption keeps going and keeps on, less and less of these sites will be vacant. They will be filled with the adsorptive moving to the surface of the adsorbent. So this type, then we will look at it in a second, where the slope initially increases as we increase the concentration of the adsorptive in solution, and eventually decreases until it becomes zero. It flattens out. We will look at the curve and see how does that look. This type of isotherm indicates that at low concentration, the surface has a low affinity for the adsorptive, which increases at higher concentrations. So what does it mean if the data fits this type of the isotherm? It shows that the concentrations at low concentrations in the solution, the surface has a low affinity. Affinity is how much they like each other, the strength of attraction between the adsorptive and the adsorbent surface for the adsorptive, which increases at higher concentration. So from the name of it, S, you can see why we call it S-shaped. It's like an S. So this is how the slope changes. Eventually, if it keeps on, if we keep on adding, it will flatten out. It will be, what does that mean? It becomes parallel to the x-axis. So that's why the slope is zero. If you have this as a straight line parallel to the x-axis, that means we have a slope of zero. Then we have the second type. We already named them in letters. The second type is the L-shaped. L comes from Langmuir. The L-shaped or Langmuir isotherm is characterized by a decreasing slope as concentration increases, since vacant adsorption sites decrease as the adsorbent becomes covered. Of course, we already talked vacant, and what does that mean, the vacant sites. And so as you cover more of these vacant sites and more molecules are adsorbed or ions are adsorbed to the surface of the adsorbent, of course, size decrease, less and less vacant sites will be available. So that's logical and it makes sense. Such adsorption behavior could be explained by the high affinity of the adsorbent for the adsorptive at low concentrations. So if you have low concentrations in solution, This means high affinity. That means the strength of attraction between these adsorptive ions or molecules and the surface of the adsorbent is high. Okay, the adsorbent of the adsorbed when is high at low concentrations, which then decreases as concentration increases. If you increase the concentration of this adsorptive in solution, then that will be decreasing the slope, or the affinity will be also less. So high affinity at low concentrations and low affinity at the higher concentration. Then we have, see if I can show you, this is the L again, this is a reversed L, think of it that way, L, okay, so that's where the, and it's continuous decrease, change in slope, all of them, if you continue adding, then the slope will become eventually zero, which means this will be parallel. We reach the maximum and we get to the parallel. We go back to this. The H type, which is the high affinity, that's where H comes from. Remember, H, high affinity isotherm, is indicative of strong adsorptive interaction, such as inner sphere complexes. Remember, the inner sphere complexes we said are very strong, and the type of forces are very strong, covalent and ionic bonding, if you remember, if you studied your earlier lecture. Okay, so again, let's look at it. This is the H type. Okay, so you can see very high adsorption. At anything you add, it's all adsorbed. Remember, this y-axis indicates the amount that is adsorbed on the adsorbent surface. So this, all what you add here, it goes to the surface. Very high affinity. It doesn't leave much, so you don't have that L-shaped or S-shaped, and the slope keeps up. It doesn't slow down like the other ones. We'll go back. The last type, the C-type isotherms, they're indicative of a partitioning mechanism whereby adsorptive ions or molecules are distributed or partitioned between the interfacial phase and the bulk solution phase without any specific bonding between the adsorbent and adsorbate. We will see that this is a straight line partitioning. Partitioning, it means division of that adsorptive in two phases. One of them is the interfacial phase, which means it went to the surface of the adsorbent, and the other part stays in solution. So it doesn't have a slope, it's a certain constant slope. Partitioning, regardless of the concentration, will stay the same. This is a C curve. So you can see that it's the same straight line. That means the percentage always the same. How much goes to the adsorbent surface and how much stays in solution as we increase the concentration is the same. Sorry. Okay, one should realize that adsorption isotherms are purely descriptions of macroscopic data and do not definitely or definitively prove a reaction mechanism. What does that mean? Big words, but we will try to explain it in simple words. When you have your data fitting any of the adsorption isotherms that we looked at, what they are describing what's happening at a macroscopic data. That means larger scale. We're not going to the molecule level at the low level of in what is happening at the surface, but they do not definitely prove a reaction mechanism. It does not indicate that this is a proof. If they fit the L shape, S shape, you can say that now we know that adsorption is only happening, and this is what's the mechanism that's holding these adsorptives on the adsorbent surfaces. Mechanisms must be obtained from molecular investigation. That's what they said, macroscopic, descriptive. From the data we look, increased, decreased, this is how much this appeared from solution. But if you study using spectroscopic, you remember we talked about X-ray, spectroscopic X-ray earlier in the course. If you use that type of instrumentation and go to the molecule level, then you can tell what is holding these on the surface. You can tell the exact mechanism, what's happening there. But from this type of data that we get from isotherms, you cannot say exactly what is the mechanism that's taking place. Thus, that's a result. The conformity of experimental adsorption data to a particular isotherm does not indicate that this is a unique description of the experimental data and that only adsorption is operational. Again, you have to concentrate when you study these. It's an all-in-one book, but I will also explain it again and slowly. Thus, conformity, the word conformity, that means if you carried out, we will see how we carry out an experiment of adsorption in the lab a little later, but that's what it means. You carried out an experiment and your data, what you obtained, confirmed. That means you could identify it. It fit the one of the isotherms that we saw. That's the conformity. That's the meaning of conformity. These data you got fits one of the isotherms that we just talked about. Thus, the conformity of experimental adsorption data to a particular isotherm, one of the ones we talked about, that does not indicate that this is a unique description of the experimental data and that only adsorption is operational. We cannot conclude that, like we said, this is kind of related to what we said here. You cannot say that only adsorption is taking place. We know for a fact this is the isotherm that explains everything. No, they confirm it. We can learn a lot from that conformity, but it does not and cannot say that only adsorption is taking place. Operational, that means it is taking place, it's happening. That means there might be other processes happening at the same time as adsorption. One cannot differentiate between adsorption and precipitation using an adsorption isotherm. So if your data had conformity to one of the adsorption isotherms, you cannot say there is no precipitation which is happening on the surface. Remember when we described and we defined adsorption, we said it does not include precipitation. But these isotherms, just by plotting your data and say, oh, they fit this type of isotherm, it does not tell you that and cannot prove to you that there is no precipitation taking place. So one cannot differentiate. We cannot make a difference between what's happening. It could be both adsorption and precipitation happening. It could be adsorption only. We don't know. We cannot differentiate between these two using an adsorption isotherm, even though this has been done in the soil chemistry literature. Now, this author, the author of the book, says that many scientists mix things and they talk about the adsorption isotherm as the real mechanism. When you have conformity to a certain isotherm, they say that that means adsorption is the only thing that's taking place. In his opinion, this scientist is a very good scientist. He says, no, we cannot judge from this type of data. Now, we've been talking about how we have seen the conformity of data to a certain isotherm. So how do we get the data? How are experiments carried out in the laboratory? So conducting an adsorption experiment. Again, concentrate, simple, but concentrate with me. Adsorption experiments are carried out by equilibrating. How we do the equilibration, by shaking or stirring. That's the method we do to get to equilibrium. An adsorptive solution of a known composition and volume with a known amount of adsorbent. As we go, I will explain the details of that. So, what do we mean by that? So again, I will read it. Absorption experiments are carried out by equilibrating. How we do the equilibrium? By shaking or stirring an adsorptive solution of a known composition and volume with a known amount of adsorbent. So let me explain it simply. We bring in, say, a certain type of flask, Erlenmeyer Flask. I'm sure you have seen and known what's an Erlenmeyer Flask in your labs, or beaker, or any glass container from the lab. So you put in that a certain known amount that means the mass of it is known, of an adsorbent. This adsorbent could be activated charcoal, it could be a clay, it could be in many of the things that can absorb things. And then you surround it with a solution, you add to it solution of known concentration of the ion or molecule you are going to have to be absorbed on that adsorbent. I'll say it again. So you bring in a beaker or an Erlenmeyer flask, some kind of flask, you weigh a known mass of adsorbent. That's the material that's going to absorb the molecule or ion from solution. And then you have several solutions. Each one of them has different concentration of the molecule or ion you are going to have to be absorbed on the adsorbent. So we have a series, many known compositions, that means known concentrations. And also in each one of them, the volume is fixed. It's the same volume. You can't have a series, each one of them has a different volume. All of them have to have the same volume, an exact known amount of adsorbents, okay? So you put those group of them, each one of them has different concentration, same amount of adsorbent, and then either by shaking on a shaker or stirring, using stirring procedures with the stirring bars or whatever. There are so many different ways to stir up things. And why do we that? To make sure the equilibrium has arrived. What does that mean? That means no more ions or molecules will be moving from solution to the adsorbent surface. That's at equilibrium. The adsorbent took all it can take, so that it reached equilibrium. And what remains in that solution, remember we started with a known solution. Later we will look at the equation. So remember these. The known composition is your initial, what you know you added to that solution. Okay, that's a solution of known concentration. We have a series of them of increasing concentration. At equilibrium, each one of these concentrations will decrease because some of it went to the adsorbent surface. Okay, so now we have two different values. We have the equilibrating at equilibrium, what is the concentration in solution, and this, the mass of this one is known. So remember when we started saying the isotherm is that graphical representation of the concentration at equilibrium. That's what we mean at equilibrium now. And what has been moved or absorbed on the adsorbent surface. At a constant temperature and pressure for a period of time, so you shake it for some time, this time the shaking or stirring might take an hour, half hour, sometimes hours, sometimes days, sometimes longer than that. It depends on what you're dealing with. So this is not a fixed time until you get equilibrium, such that an equilibrium absorption reaches a steady state. Steady state, that means no changes, no longer changes after period of time, finished, is attained. No changes happen. We have attained, we have reached an equilibrium. That means the concentration in the solution now became constant. The pH and ionic strength are the pH and ionic strength are also controlled in most adsorption experiments, because pH, ionic strength, we already know. Remember, in salt solution, we studied the ionic strength and we know what it is and you know how to calculate it. So the ionic strength, the pH also have to be known and we control them. You have to say all the conditions at which you carried out your experiment. After equilibrium is reached, the adsorptive solution is separated from the adsorbent by centrifugation, settling, or filtering, and then analyzed. Because remember, at equilibrium, of course, they find out by taking samples at different times until they know that it's not fixed. So by that time, they know how long they need to do this experiment. So at equilibrium, if it's reached, after equilibrium is reached, the adsorptive solution, now we have a solution, and remember, we have a mass of the adsorbent in that same container. You have to separate them from each other so that we can analyze the concentration of the solution. So you separate them. How would you separate them? There are several ways, either by centrifugation, settling. There are settings that you just let them settle for a long time, or filtering, using different types of filters to separate the adsorbent, the mass that's in that container in the flask, and the solution. And then we analyze the solution. That analysis will give us the concentration at equilibrium, how much of that remained in solution after that time that we shook them, shaking, stirring for certain length of time. The method that one uses for the adsorption experiment, example, batch or flow column, is also important. We have two different types of experiments. Batch is like what I have described to you. You put the things in a flask, the mass of the adsorbent, and you put the solution of the adsorptive, and you shake them for length of time or stir them. That's a batch system. But also we can pack the adsorbent in a column, glass column, okay, cylinder, whatever that we call it, a column. You pack that material and you pour the solution that has the adsorptive on top of that and let it go down. And at the bottom there will be an outlet. You take samples from that to see that it reached equilibrium. So they are used, both of them used for different purposes and for different accuracies and whatever. We're not going to go through that, but you should know there are two types of this type of experiment, either batch, the batch is like what I explained in detail, or the column I just have also told you about it. Okay, how do we do the calculation? We talked about it. Now we will look at the actual equation. What do we do? One can determine the degree of adsorption by using the following mass balance equation. Okay, C0 V0 minus, remember, you put parentheses, CF VF over M equals Q. Rather simple, just concentrate. We'll look at these, what do they mean, and then we'll go back to the equation. Q is the amount of adsorption, adsorbate per unit mass of adsorbent. The units in here in mole per kilogram, but they can be anything. They can be microgram per gram, milligram per gram, depending on how much the adsorptive can be attached to the adsorbent. What is the affinity between them? This has different ways. So, but this is a unit. Remember, it's mass per mass, because that adsorptive moved to the surface. Now it's not anymore in a solution, so it has to be mass per mass, mole per kilogram, microgram per gram, microgram per kilogram, whatever it is, units, depending on what type of experiment you're running. So Q, always remember, is the amount of adsorption that took place, adsorbate per unit mass of adsorbent. C0 and CF are the initial and final. Why we call it CO? Some people call it CI. If you see it anywhere, CI, initial. C0 from time zero, before we start the shaking or the stirring. That's C0. The time is zero. And F is the final when we stop the experiment. So C0 and CF for final are the initial and final adsorptive concentration. How much we started with, we know, remember, we put known solution concentrations and inside it or with it the adsorbent mass, which is known. So again, the concentration mole per liter. Remember here, surface mass to mass. Here we talk about something in solution. So this is mole per liter. V0 and Vf are the initial and final adsorptive volumes. So the volume, remember we said it has to be a known value, and usually that known value is the same. The volume really doesn't change. Although we call it V0, Vf, they are the initial and final adsorptive volumes. They are usually the same, respectively, in liters. And M is the mass of the adsorbent in kilograms. Remember, so this will say how much was adsorbed. That's the adsorbate over M. You divide it by the mass you started with of the adsorbent, and it will give you Q. So how much of that moved from solution and became adsorbed, which is the adsorbate, per mass of the adsorbent, that's Q. And this will be always in all the equations we will see, it's the same thing. Remember, it's Q. Adsorption could then be described graphically. Then we can plot by plotting CF, where CF is the referred to the equilibrium or final adsorptive concentration. Remember, not the initial we started with. After we stop the experiment and we measure the concentration, which is the final concentration, okay, so that will be the concentration we take, the final one, the equilibrium concentrations, CF at the end, where CF is referred to as the equilibrium or final adsorptive concentration. We put this on the x-axis versus Q, which we calculate from this equation, on the y-axis. Okay, we look at two. There are in your textbook many adsorption isotherm and many equations. Only concentrate on the ones I will explain to you. I will explain to you two of those isotherm equations only, and concentrate on this. These will be the only ones that you require to know. Don't ignore all the others, because this textbook, I use it for both undergraduate and graduate courses. So that's beyond, some of that material is not really for you. Okay, there is an array of equilibrium-based models that have been used to describe adsorption on soil surfaces, an array mini group. These include the widely used Freundlich, some people say Freundlich, I think it's a German name, used Freundlich equation, a purely empirical model. And then we have the Langmuir, we already remember we saw the L, we said Langmuir equation, and the double layer models, including the diffuse double layer, Stern, and surface complexation models. All of these, don't worry about them. We will concentrate only on Freundlich and Langmuir. Okay, what's the Freundlich equation? Q, remember, Q, we already know what it is, equals K of D, C to the 1 over N. Q and C were defined earlier, remember. In the general equation, how we do the calculations, we already defined what's Q in the previous slide. So we know what's Q and we know what's C. KD is what we call the distribution coefficient for this particular equation, for the Freundlich equation. N is a correction factor. So these are constants that belong to this equation. And these constants change, sorry, they're constants for your experiment, for the experiment you ran, not constants always. If they were constant always, then they will have certain number, and then we will memorize that number, and that's it. But we call them constants. They will be constants for that particular experiment you're running. So Q equals KDC to the power 1 over N. So we know what all of them know what they are. Now, this type of equation, to plot it is difficult. So what we do in this particular, we take the logarithm to have the linear form of this equation. To have the linear form, we take the log of both sides. Log Q equals log KD plus, remember, the log of multiplication of numbers, the addition of them, the addition of their log. So, and then the power comes before the log. So you have log KD plus 1 over n, because it's the power to c of log c. This is the linear form of the Freundlich equation. This is the original. This is the one we can plot, which is the linear form. How do we get the linear form? By taking the log of both sides. If this side equals this side, of course, the log of this side will equal the log of this side. The slope, after you do it, remember, this is a straight line equation, like y equals, say, a plus bx. Okay, similar. You've known the equation for a line. So the slope, remember, this always, the constant is what we call the intercept, where the line intercepts the y-axis. That's the value. We call it the intercept. Okay. So 1 over n, and the intercept, this is the slope. Remember, this one is the slope, and this one is the intercept. So now we have defined the line. If we know the intercept and if we know the slope, you can draw that line. This is how it would look if you do it. So this is the equation we said. Okay. Now, if you see in some F, sometimes some people, instead of D, we just said D on the other page or the other slide, but it's the same. Some people write it to indicate that it's the Freundlich. It's the constant of Freundlich. Okay. And the same thing we said, you do this, you take the logarithm to get the linear form, and this is how you draw it. And the main thing, what do we need to find? We want to find the values of k and the value of n, because these are the unknowns. These values from our experiment, we have them. These, the q and c from our experiment. The series of q and e, those points here and here, we get them from our experiment. So what do we need to find out? The value of k and n. And we said k is the Freundlich constant. Remember, here log k is the intercept. You draw this all the way. Where does it intercept the y-axis? The value that will give you log k. Then from that you can find the value of k. And then 1 over n is the slope, and then n will be 1 over the slope. Okay, the next one of the major disadvantages of the Freundlich equation is that it does not predict an adsorption maximum. This type of equation cannot tell you how much the adsorbent you have is capable of holding of that adsorptive, the particular adsorptive you're working with. The single, single KD term in the Freundlich equation implies that the energy of adsorption on a homogeneous surface is independent of surface coverage. That means the attraction of any molecule or any ion to that surface is same. It doesn't matter how much coverage. Is it at the beginning of the experiment, near the end of it, half of it full until it reached full coverage? It doesn't matter. The same affinity. Another widely used absorption model is the second one we talked about, is the Langmuir equation. It was developed to describe the adsorption of gas molecules on a planar surface. Where is the origin of these? None of them was ever used for soils to start with. Most of these were done by physicists and some other scientists. The Langmuir equation was description of the adsorption of a gas on metal surfaces. But then later it has been used by so many environmental scientists, including the environmental soil chemists. It was first applied to soils to describe phosphate sorption on soils. Since that time, it has been heavily employed in many fields to describe sorption on colloidal surfaces. As with Freundlich equation, it best describes sorption at low sorptive concentration. Most of these adsorption, remember, we cannot have precipitation and call it adsorption. So most of them you deal with very low concentrations. The original assumption that Langmuir made in the development of the equation, he made some assumptions. It's not just you can apply it anywhere you want. Adsorption occurs on a planar surface that have a fixed number of sites that are identical, and the sites can hold only one molecule. It's simple. So it tells you that you have a planar surface, like a plane, horizontal, that have a known exact number of sites that can hold or attract the molecules or ions, and the sites can hold only one molecule, so one molecule or one ion for each site. And all these sites are identical, no differences among them. Thus, only monolayer coverage is permitted, which represent maximum adsorption. So when you cover all the sites, or when all these sites are covered, that's a monolayer covered. No more, you cannot put any more ions or molecules on that surface, but it's full. So we call it monolayer coverage. That means you cannot have another layer on top of the first layer. You have only one layer, which is exactly attached to the adsorbent surface. Okay. Then adsorption is reversible, which means things can leave the sites, go back to the solution, and vice versa. So it's reversible. There is no lateral movement of molecules on the surface. After one molecule or ion takes this one side, it cannot move to another. It cannot exchange with another side. That's it. So no lateral. Lateral means from one horizontal place to another. The absorption energy is the same for all sides and independent of the surface coverage. So we said the places are identical. So how strong any site holds a molecule from that adsorptive we have is the same. It doesn't matter where it is on the surface. They are all the same. So, and it's independent of the surface coverage. It does not change as the more adsorptive is on the surface. Say you covered 50% of the surface, 90% of the surface, the same energy stays the same. And there is no, these are assumptions, remember. And there is no interaction between adsorbate molecules. It means the adsorbate behaves ideally. So these molecules that were adsorbed on the surface of the adsorbent, they don't interact among each other. So they behave ideally like the ideal gases you remember you studied in physics. Most of these assumptions are not valid for the heterogeneous surfaces found in soil. If we try to apply all these assumptions to soil, actually most of them really do not apply to soil, because from our studies, if you remember, soil colloids, I'm not going through all of these, but if you go and compare these to what we have studied about the surface of colloids, whether humus, whether silicate clay minerals and all that, none of them really can be applicable in these cases. So all these assumptions are ideal assumptions, and yet people use them because they can utilize them and get some kind of information. So although most of these assumptions are not valid for the heterogeneous surfaces found in soils, as a result, the Langmuir equation should only be used for purely qualitative and descriptive purposes. So it, like I said, and we have already read, it gives you information, but it does not give you mechanism. It does not tell you that 100% you have adsorption happening in the soil. Okay, sorry. Like we did with the Freundlich equation, we look at the equation of Langmuir. Now, if you happen to see in your textbook or in many textbooks different forms, there are more than one form of this equation. Sorry. Okay, more than one type of this, but they're all called sorry, Langmuir equation. So it does not make any difference. Usually when you are given this, you will be given the linear form because it's very hard for you to derive. It's not like the other one, take the log of both sides. The other one, you need to do it on your own. But this one, usually you will be given the linear form because of the different forms of Langmuir absorption equations, where Q and C are defined previously. We already know. Whenever you see Q and C, we know what they are. K is a constant related to the binding strength, and B is the maximum amount of adsorptive that can be adsorbed monolayer coverage. So this particular adsorption isotherm, we can find the maximum, how much this adsorbent can hold of that adsorptive. That is the maximum. It is one of its constants, so we can find. Remember, Freundlich equation did not have a maximum. This one you can obtain a maximum from it. So these are constant, but this constant, the B, is the maximum, which is the maximum amount of adsorptive that can be adsorbed per mass of the adsorbent. Rearranging to a linear form, okay, like I said, so you don't have to do that. This will be given to you. If I give you in the exam, I will give you and tell you this is the linear form. Now look at the linear form, you have to know what you can plot. C over Q, both of these are variables. So C and Q, remember from our experiment. So this C over Q is 1, like saying Y. So this C over Q, it's the ratio, but it's like Y. This is Y on the Y-axis, okay? And then you have C, okay, C on the other axis. So plotting C over Q, this is Y, and C versus C on the X-axis. This is the Y-axis, C is the X-axis. These are constants, all of the others constant. Then, again, just like we said, this is linear form, so Y equals, this is the intercept, okay? 1 over KB is the intercept, so you find the value of the intercept. So 1 over KB now is known, and then C1 over B is the slope, remember, 1 over B is the slope, so 1 over the slope, the value of B. So now we know the value of B. We know the value of 1 over KB. You put the value of B here, and from the intercept value, you can also find the value of K. So now we can find the value of the two of them, the two constants. And the B, remember, is the maximum amount that the adsorbent can hold. We'll look at the equation drawing. We do the same thing. Okay, again, like this is a different, it can be different from the other, like the one previous one, it doesn't matter where, but there is always, you will be given a form and the linear form, or you will be given only the linear form. So regardless of the form, there are several forms, and each one of them, the linear form is different. But you concentrate on the one you are given. It doesn't matter what. Again, Q is the amount of adsorbed per mass unit of adsorbent. We already know that. CE, sometime, remember, we always sometimes call it F, C final, or CE equilibrium. Also, same thing, is the equilibrium concentration of the adsorbate remaining in solution. KF is the Langmuir isotherm constant related to the capacity of saturated monolayer. B is the Langmuir isotherm constant related to the energy or enthalpy, remember, which gives you the maximum amount. We said this is the maximum amount that can adsorb. So this way, we finished the chapter and we finished this lecture.